I started.
Okay.
Yeah, sorry. Could you clap?
Wait. Okay. 3, 2, 1. Okay.
That was
Cool.
good enough.
Welcome back to episode 3. I put a 3 of shush. Of the Brown Boy podcast. Still looking for a name.
What's wrong with the name, man? Everyone likes it.
I just don't like it. My mum doesn't like it. I don't know. It's a bit strange. We need to find a unique name. I don't know. Huh?
My mum doesn't mind the name. Actually, I think she hasn't made a comment about it yet. She watches the video, ish.
Does she?
Or like the first 2 minutes, maybe.
Yeah, everyone watches. On average, people watch 3.5 minutes to 5 minutes. Last time, I think one person or no one finished it. Like someone got to 46 minutes and just like, no, I've had enough. And so that's it.
I bet it was like Vivi or Arin as well.
Yeah, someone we know probably. But they really stuck it out, so thank you. But the timestamps did help. I know I didn't tell you, but like I had a little clip at the beginning where I told people about timestamps. So they'll in the description there will be timestamps to whatever we're talking about. And I saw that helped, viewership across, audience retention or whatever. So again, timestamps in the description. And I guess we'll jump into it. So, what are we discussing today?
I believe I have a quote.
Mm-hmm.
So this is the new Stephen Hawking book that I have got in my shopping haul, and yeah, there's just something. There's a paragraph in here. It's just one sentence, but it basically embodies why we do this podcast. Because so I'm just gonna read it out. At the end of all this, the fact that we humans, who are ourselves mere collections of fundamental particles of nature, have been able to come to an understanding of laws governing us and our universe is a great triumph. I want to share my excitement about these big questions and my enthusiasm about this quest.
He's a very cool guy. I mean, yeah, he's not wrong. I think, despite the fact that in the grand scheme of this, maybe none of this matters at all, we should still celebrate the fact that we're able to, discover things, learn, find out, how things work. And it's built into us, but it's also a triumph of science and a triumph of knowledge and understanding. And, it helped us move forward.
Yeah.
So, yeah.
Let's begin.
Cool quote to begin with. Actually, I have some other books. I forgot to go through them. So hopefully we'll have some more book-related stuff in the future. Did you start another book? Or have you finished that one? Or
Finished? I'm like 2 chapters in.
Oh, okay.
I am not a quick reader.
Yeah, neither am I.
Can we get started already? Now?
Okay. So, you wanted to discuss how we measure the mass of the universe. Yeah. Right, so it seems like a bit of a daunting question because, I mean, first of all, if we look up to the sky, there's millions and billions of stars and planets and galaxies. So first, how do we count that up? How do we account for things we can't see? Perhaps the universe where things aren't like all illuminated, or the extension of the deep universe where like light may not even traveled there yet. So how do we calculate the mass of the universe, and how can we verify that the mass we calculated is true? So, well, we start off by getting a target. So how much mass should we expect? And we can actually kind of estimate this based on the Big Bang and the ratio between different elements. So you're probably familiar with hydrogen, helium, and deuterium, right?
Mm-hmm.
So deuterium, I think it's hydrogen with a neutron, right?
Yeah.
Yeah. So there are ratios of hydrogen to helium to deuterium in the universe, and this ratio is very stable, and it hasn't changed since the Big Bang. So the way it worked, the reason for that is because in the beginning it was very, very hot, and what happens when sort of the protons, the neutrons, and everything's really hot?
It moves a lot.
Yeah, it moves a lot. They can't sort of stick together. They can't form atoms and stuff. As that starts to cool down, what starts to happen?
They start to like slow down, start to bond together or form like stuff like more, I don't know, heavier sort of elements. Like that.
Yeah. So say we had just lots of neutrons and lots of protons. A proton on its own is basically hydrogen. But say we had lots of neutrons and protons. Eventually, over time, what would happen to the neutrons and protons, and what would they form?
They would sort of be in sort of like an equilibrium. They'll form, atoms, like nuclei of atoms and stuff.
What's a neutron and a proton together?
A neutron and a... What?
I just told you.
Oh, the deuterium.
Deuterium. We're not talking about electrons here. We're just talking about the nuclei. Okay. Because electrons are still way too fast to get involved. So as the universe starts to cool down, your protons and your neutrons start to fuse together to form deuterium. So that's fusion at the beginning of the universe. And then this deuterium quickly fuses again into helium, which is 2 protons, 2 neutrons. So basically an alpha particle. So you start off with your hydrogen. Over time, it becomes deuterium, and it quickly becomes helium, right? And then once it reaches a certain sort of like pressure and temperature, like once the universe, this was sort of like this was seconds after the universe was after the Big Bang, and then it's quickly making deuterium and helium. And then once it reaches a certain temperature and pressure, it can't fuse anymore, right? So you have your amount of hydrogen, deuterium, helium, and that's it. It's fixed. You can't do anything with that now. So it's almost like it's like a snapshot, almost like CMBR, background radiation, is like a snapshot of the early universe, and it goes all the way back to the Big Bang. In the same way, these ratios of hydrogen, helium, and deuterium, they're stayed constant. So they're a snapshot of almost when deuterium and helium stop fusing. And the ratio of helium to deuterium, I think you get, for every 1 part of deuterium, you get 3 parts of helium. So the majority is actually in helium, and then you have hydrogen, like lots of hydrogen. And so based on this, very smart people did calculations about what temperature you'd need, what pressure you'd need, and the amount of baryonic matter, so the baryons being the protons and neutrons, what ratio of baryonic matter you'd have compared to dark matter or dark energy, or like stuff like things we don't actually know how it works, but you can calculate the ratio of how much dark energy and matter you'd have compared to baryonic matter. So they ended up with a value of it's between 5 to 7%, I think. So 5 to 7% of the universe is baryonic matter. Right, so everything we see, all the stars, all the galaxies, and also everything we can't see, that's all baryonic matter, and that's only 5% of the universe. Which on its own, it's incredible. Like, what the hell? Right? Because then there's an extra 19 times worth of that in dark energy and dark matter, which is mental. And we don't even know what it is. But anyway.
Yeah. Like how they know that it's only 5%. So I'm guessing they have a calculation of what the sort of the speed of expansion of the universe is, and they can then calculate the theoretical mass of how much the universe should be if it's accelerating at a certain rate.
Yeah. So what was the rate of expansion? What sort of pressure and temperature was it in that early universe where like it was still very young? Obviously it was still huge, but it was still very young and very small compared to what it is now. And then what level of temperature and pressure you need to reach in order for this to stop happening and to reach those ratios, right? So that's the first thing we need to. That's the first established fact. 5% of the universe is baryonic matter. Now, how can we verify, and how can we find this 5%? Well, you can like, how would you go about finding everything in the universe?
Well, the only way stuff in the universe interacts with Earth is the types of radiation that come from different parts of the universe, and
That's true.
so whatever they emit, that is the only thing from which we can work out anything.
Mm-hmm.
So, depending on a certain mass of something, we can then sort of figure out, depending on how much radiation is given off in a certain direction and what kind of radiation it is, maybe in that sort of way, we can work out the mass of the universe. However, like, if you think about it, right, as if let's say you have a, what's it called, a lunar eclipse, solar eclipse, one of them two, the moon being in the middle. I forgot which one that was. I think it's solar eclipse. But when the moon's in the middle,
Mm-hmm.
right, and sun's doing up rays,
Mm.
shadow, less rays,
Yeah.
goes to the earth. The same way, some of the emitted radiation should theoretically be absorbed or like sent in different directions before it reaches Earth. So it might not be as accurate as one might expect. However, I imagine the emitted radiation to be sort of absorbed and then re-emitted, but it might not be the same way. Do you get me? Like, it's weird. Like, you see all these thoughts
Yeah.
running in my head.
No, you're getting there. You've missed the most obvious thing you can start off with.
Just looking up.
There we go.
Looking at what's,
Right,
fair
so
enough.
that's what I was looking for as a starting point. You're right, they do use those techniques. One thing I'd say is, like, say you're using the sun as like an example. How do you know how much light you'd need in the sun to start off with to then figure out how much was blocked and how much was re-emitted?
You can fly and see.
Fly.
Yeah.
Let's fly to the sun.
Mm-hmm.
Yeah.
And
Oh,
see
that's a
how
good
much of
idea.
it there is.
Let's fly to a quasar and see how much light's emitted from a quasar. Yeah.
Well, you can see. Well, if you can see on a regular day when there's no eclipse, how much sort of lux of light there is. I think that's the unit of light intensity. And then when the eclipse actually happens, then you see.
Yeah.
Yeah.
Pretty much. But yes, we start off by just looking, right? So we can look at the night sky, and we can find how many galaxies and stars are, and even black holes are in a specific area of the universe, and you can sample, and then estimate like everything that we can see ever, or everything we could see, right? And obviously it's a lot of sort of number crunching and calculations and estimates and stats and sampling, but it's possible. And we're just looking for an estimate here. We're not looking for an exact number. So sampling and sort of extrapolations, they're fine. However, we reach a conundrum. When we look up and we see, like we add up everything that we see, we only get 20% of that 5%. So we've only found 1% of the universe in terms of everything that's lit up and everything that we can see. So, what do we do now? Where is the rest?
Okay. So only
Clue
20%
in the
of-
fact that it's lit up.
Yeah. I was gonna come to that. So.
Yeah.
The reason why we may have not actually experienced this missing mass is that they might not be emitting anything for us to actually observe.
Mm-hmm.
So it's just like dark. And so this means that stuff that's not emitting anything cannot be observed. Something that's really, really cold. Are neutron stars, do they emit anything?
Yeah.
Oh. What's stuff that don't emit anything?
What happens after a neutron star? It's it goes dark. You just get like a dark star, or even black holes, or just planets that aren't illuminated by a sun.
Oh yeah.
So yeah, you're right. So a lot of the universe is actually just not lit up, so we can't see it, or the light isn't coming in our direction, which we can't do anything about. So how do you think you've already touched on this obviously, but how do you think we'd overcome that?
How do we overcome?
You talked about it like before, when you didn't need to.
Rays. Electromagnetic rays.
Yeah,
radiation.
electromagnetic radiation. So, do you know how? So obviously you've got this property of electromagnetic rays and the fact that it can be absorbed by a particle, by like an electron, and then re-emitted once the electron. So if the electron goes to a higher energy level and then drops down again, it emits another photon, right? So if you're counting that as just one ray, then your ray is essentially being absorbed, emitted, and every time it's emitted, especially when it intersects something like hydrogen, which has hydrogen, I think, has one, or like it has its most common transition state for an electron. It's called the Lyman alpha transition. Every time it's absorbed and emitted, it's always going to be the same thing, right? Every time it's emitted, it's always going to be the same color light, despite whatever light like went into the electron. So we can use this property. It's almost like we're using sort of a big backlight. So we need something big and bright in the universe, and then as it's coming towards us, it's not going to come out just like as a straight line with like unintercepted. It's going to come across celestial objects, matter, and then based on that, so if it comes across hydrogen, it will be absorbed by that hydrogen, or the electron in that hydrogen. The electron would bounce up and down an electron, and then it would be re-emitted again, right? Mm-hmm. So if we measure this light from a quasar is what we use, because it's like it's sort of a I think it's sort of a supermassive black hole. It's the accretion disk of a black hole, which is like super bright, or it's sort of a large event where sort of two black holes collide, or a star and a black hole collide, or just sort of like these huge events that emit lots of light and radiation. That light comes towards us, and as it encounters matter, hydrogen most commonly, but also other matter, we can see that like where it's been absorbed in the absorption spectra. So you do chemistry, right? So you know how they have emission spectra and absorption spectra.
Yeah.
For like what do they use it for?
They do it for, well, you can look at sort of structures of different molecules. For example, DNA crystallography and diffraction of benzene, for example. Basically, it's all about excitation, de-excitation of the electrons, and like how much radiation they emit. I mean, how they're emitted and everything. What's
the thing where they figure out what materials are in like an object or in a gas?
Well, you can have spectroscopy, so
That's
mass
it.
Spectroscopy.
Yeah. So it's almost like spectroscopy or spectrometry or whatever it is. Where
Spectrometry. What the flip did I say?
Spectrometry.
Spectrometry. Okay. That's the word.
You can sort of like see the absorption lines, and then from that you can infer what materials are in the gas, what isn't in the gas. In the same way, when you measure the absorption spectra of a quasar from deep space, or not deep space, but from space, you can see where it's been absorbed. And because whenever it's absorbed and emitted, it's always going to be at the same wavelength. But then you can see dips in different parts of the wavelength spectra, which means that there was mass further away, and as it came to us, it got redshifted, or it was mass closer, which had less time to get redshifted, right? You're familiar with redshifting.
Yeah.
So basically, from that, you can infer how much matter it came across on its way here. Right, so this is matter that it's not illuminated, we can't see it, but we know it's there because it's been absorbing and emitting electromagnetic radiation. Now, from that again, if we take multiple readings of different quasars and different events in space which emit a lot of radiation, we can also then we can calculate how much mass is in the universe that we can't see at all, right?
Mm-hmm.
So how much extra universe do you think we've discovered?
I'm guessing there's still a missing piece, so I'm going to say like 40% more.
We found 20% last time. 40%, you're close. We found about 35% of the universe now. Extra. So we were at 55. Okay? So we found half. We found half the universe in matter that we can see and in matter that we can't see. So, where's the rest?
By chance, we might not have actually come across it yet.
Yeah, you're right. On the right lines.
So,
What
Yeah,
is in these the methods that we're using? So we're using sort of it's reflecting light, which means it's a massive object, as in it has lots of mass and it can reflect light. Or we're using the property of electrons bouncing up and down electron shells. So what could be an exception to those two things, or specifically one of those two things?
What, like black holes and stuff?
No, we can see black hole. We can measure black holes. We can find their mass.
So stuff that are an exception to electrons excitation to excitation.
Yeah. So why might it not have this property?
Because they don't have electrons.
Yeah. No, you're right. So why would something not have electrons? This goes back to, say, in the early universe, why did the protons and neutrons not have electrons surrounding them?
Because it was something about it being either too cold or too hot or something such that the electrons can't actually be revolving around like a nucleus because there's no nucleus.
Well, I mean, the protons and neutrons are basically the nucleus. But yeah, it's too hot, right? So the protons in the early universe were sort of like moving around at such a speed that, and the electrons were moving around at such a speed that they couldn't attach together or come together, whatever. They couldn't form atoms yet. So they ran computer simulations of this. They couldn't find the rest, so they ran a computer simulation of the early universe based on hydrogen, deuterium, helium, how much mass should be there, how much dark energy and whatnot. I think we know how dark energy, the properties of dark energy. We just don't know what it is, I think. But they basically ran simulations on a computer, and they found that a lot of the matter it wasn't collapsing into planets or galaxies or suns or black holes, but it was just matter in between galaxies and in between black holes and planets and stuff like that. So because I don't know why, but apparently if you do calculations, you can actually infer that a lot of the mass wouldn't be stable enough to form planets and suns, but a lot of this is just matter that's in between galaxies. So
it's the idea that space isn't a perfect vacuum. There's always like particles like here and there.
Yeah, well, technically, a lot of space is almost a perfect vacuum, but yes, a lot more of space is actually filled with matter. And the thing is with this matter is that it's actually between 100,000 to 1,000,000 Kelvin, right? So it's actually like superheated. So
How?
I don't know. It just is.
I don't.
But
So how is it super hot when it's not doing anything? Like it's not.
I think it's either been
powering
emitted, or there's sort of somewhat of an energy transfer in between it. But it's basically just plasma out in space, and it's just there. And obviously it's not super hot, but it's also not cold. So they call it warm hot, and it's called the warm hot, the warm hot intergalactic medium, or the WHIM. The WHIM.
The WHIM.
Yeah, it's the WHIM. WHIM. And so now,
And I love physicists. You know why? Like you see a hole in space that's just dark, and you call it a black hole.
Yeah.
And like calling this a WHIM. That's funny.
it's called the WHIM. So now, what do we need to do? We need to find the WHIM. So how do we find the WHIM? So yes, the problem with this is that it's plasma. So the electrons aren't attaching to sort of the protons and the neutrons. They're not forming atoms, and because of this, it can't absorb and re-emit electromagnetic radiation. So what can we do?
We can shoot stuff at it, so it can shoot stuff back.
What are you shooting?
I don't know, something. If you can shoot something, right, and make it excite somehow. So basically, what I'm saying is, if nothing is reaching it, oh no, wait, but that's gonna basically stuff really, really far away. it will take like ages for it to go there and come back to us. So that's not
Yeah.
gonna work. Okay. So what I was initially thinking is like you can, if nothing is hitting it for it to re-emit anything, you can shoot stuff out so it can re-emit back to us. But that's stupid because there's nothing there. And like it will take too long. So our goal, right, is to find a way to be able to detect these particles which have nothing emitting to it.
Technically, they are still illuminated. They're just so dispersed and so small that we just can't see them.
Nice.
So,
well, you can make a sample of somewhere in space and try to multiply it by the whatever volume you can be observing. So, go to space again, right? Go fly away, or you can simulate a vacuum on Earth. I guess that's a better idea than flying to space or something. And then you can see how many particles there are in a certain volume of space. And yeah, you do up. I think. I don't know. I'm just saying. I'm just chatting west now.
you're not wrong with the samples of space. You're getting somewhere. You're actually getting this. This is actually actually pretty hard physics and like theoretically, but yeah. So what they did is, like I said, this stuff is technically it's illuminated, but when you try to look at it and like see how much mass there is based on the way it interacts with gravity, the amount of light it's emitting and whatnot, it's very, very inaccurate because it's such a small amount of mass. Like in small quantities, it's such a small amount of mass. Obviously, when you have the entire universe and all the galaxies, then all of that adds up. But if you're looking at just two galaxies together, it's very, very hard to detect that mass. So they need to find some kind of way of amplifying. Like if they take a picture of two galaxies close together, there is a WHIM in between them, right? So, don't laugh. He laughed.
Yeah.
Okay.
Yeah.
There is a WHIM in between them, but it's so like the effect of that mass is so light that it's very inaccurate. So they need some kind of way of amplifying this. So I'll just go straight into it. There's no point. It's going to take way too long. But
yeah, I'm bad.
They took lots of pictures of two galaxies together, right? And it's not just of like one pair of galaxies, but they took lots of pictures of lots of pairs of galaxies. And they oriented it in such that the two galaxies in the frame were in the same place. And when you layer them on top of each other, you basically get a very, very bright image, which is basically all white or very, very much orange. But if you then remove the mass of the two galaxies, so they tried to basically infer how much mass would be actually in the galaxy, in each of the galaxies in all of the pictures. I think they took about 1 million samples, and once you layer all those pictures on top of each other, and you took away the mass of the galaxies, what you were left with is the WHIM, the plasma, right? So you could actually see. So they basically saw. I'm not gonna say it anymore. I'm just gonna say they found the extra mass. They found the extra mass, and they basically multiplied it by 1 million, and then you can finally actually see it. They basically multiplied the amount of light that it was reflecting by 1 million, so that you could just see it, right? So that's what they did.
Oh, yeah.
But it was a bit dodgy, so they needed to verify it again, because it was very uncertain, because you were taking a lot of estimates about how much mass was in the galaxy and stuff like that. So they tried again. So obviously this was one of the theories, and obviously the people that were involved in this were like, yeah, we found the rest, but more people needed to be more convinced. So now this is the really genius bit. I'm going to talk about lightning. So lightning on Earth. I need some water. One sec. Okay. Lightning on Earth.
Cool.
Lightning on Earth. When there's a lightning strike, you can see it, right? And you can measure it using electromagnetic signals, right? And you can see it when you're close by and hear it. But a lightning strike actually emits radiation across all parts of the electromagnetic spectrum, magnetic spectrum. So and this goes out in all directions. So yes, there is some light coming towards your direction and then all the viewers' directions when like the strike happens, but there is also radiation going into space. And these waves are guided along. They're guided along the field lines of the Earth. You know how the Earth is basically a magnet.
Mm-hmm.
It's got North and South Pole, and these field lines, once they go out into space, they don't all just go out into like space. Some of it is directed along the electromagnetic field lines of the planet, and then they go around to the other side of the Earth, and you can actually measure this radiation. So every time a lightning strike happens, like on the North Pole, you can still measure it at the South Pole, even though you couldn't see it and you didn't know what happened or when it happened, but you can actually measure it, right? So when you have this radiation, in the same way that light is sort of, it's redshifted when the two objects are moving away from each other, right? In the same way, this light that's going around the field lines is dispersed, and the shorter wavelength is dispersed less than the longer wavelength. So basically, the wave stretches out, and if it stretches out enough, then it sort of creates copies of itself. And then when you listen to it, it's not a lightning strike, but it's more of like a descending whistle sound, right? It's this strange behavior that happens with it. But the good thing about this is that when it interacts with the matter and it gets dispersed, it's not interacting with electron shells and electrons. It's interacting with ions and charged particles, right? Because it's sort of like it's delving more into the electromagnetic part of the magnetic spectrum. So it's when it's dispersed, it's interacting with ions. Now, what is plasma made out of?
Really hot ions.
Ions. So, if we take the same principle with lightning and we apply it to space, again with radio waves or quasars or whatever it is, then the light getting dispersed, which we don't account for first, because first we're just looking for absorption and emission spectrum. But now if we account for the dispersed light and the dispersed waves, we can measure the amount of ions that it comes across, which is the remainder of the mass of the universe. And I don't know why, but I think we can only do this with radio waves. So we need radio waves to do this, because I think with radio waves, then it's first of all, it's a longer spectrum of radio waves. It's a much smaller range, and also the dispersion effect is much more pronounced than other spectrum. Anyway, we need radio waves for this. And as if on cue, I think it's 2007, either 2007 or 2017, or somewhere in that range, very recently, we detected a burst of radio waves from somewhere in the universe. So it was like deep space. We don't know where it came from. It just happened. And this happens again and again and again. Not from the same place, but just from different places. We just get radio waves from nowhere. And it's coming from deep space. And based on the amount that the wave has been dispersed, we can then infer how many ions it came across and how much matter it came across, right? So, but the dispersion with hydrogen is less, so they actually look for things like oxygen ions and things like that. And because this oxygen is sort of like a tracer for more hydrogen in that same area. Anyway, what you can do is, with the rate that these radio waves have been dispersed with, and if you take samples again and again and again of different parts of the universe, then you can calculate how much plasma, how much matter there is in between galaxies. And this is the remaining 50% of the universe. And
Oh, thank gosh.
Yeah, and it's actually a very recent discovery. So until very recently, we didn't know where it was. We didn't know where the universe had gone, and yeah, I think it's a triumph of science that we can actually measure the mass of the universe, and I think that's just crazy.
And the rest is just dark energy, dark matter. Oh, the sky's nice. Anyways, yeah, dark energy, dark matter. Yeah, you mentioned something interesting. Remember, like when we were talking about different timelines just being spawned out of nowhere in the previous episode, right? And you said, oh, maybe this energy is coming from dark matter, dark energy, but I'm thinking, right? If it keeps on happening, how comes the mass of the universe doesn't decrease?
Well, maybe it does, but it's going down such a small rate that we can't detect it. Because when you think about it, if you're spawning millions and billions and trillions of timelines, and you need energy for that, you wouldn't have sort of, if you have like a bank of energy in dark energy, you wouldn't have it such that, like, we're assuming that it's been created with sort of an idea behind it, but you wouldn't have a bank of dark energy such that you can measure it being depleted. Like, if you could look at a bank account and see it going down, then, like, obviously that's not a lot of money. But if you look at $1 billion and someone's removed $10 from it, like, you wouldn't notice, right, in the grand scheme of things. So I think maybe this, like, dark energy and dark matter is just like hyper concentrated energy, such that when it's like spawned another timeline, we don't know. Again, complete waffle. That's just off the top of my head. But yeah, maybe. Yeah, it's interesting.
If we're just correct by chance, then
yeah,
we must.
The fucking infinite monkeys thing.
Yeah. Anyways.
Right.
What we also need to talk about, what was this? The butterfly effect or something you had in mind.
Yeah, the butterfly effect. So, do you think that the flap of a butterfly's wings in Brazil can cause a hurricane in Texas?
By chance, yeah. I mean, that's how it works. Definitely, I think. It's like, it's not just that one. Actually, I don't know. It might be just by chance. Like, the flap of a butterfly wing, the displacement of air particles and the changes in pressure can perhaps like be added on and on, just causing a knock-on domino effect, like increasing the changes in the pressure, like with the air.
Yeah.
I forgot from GCSE geography how like
that's not important, but yeah.
Yeah, and just said the whole GCSE is not important. Okay. Anyway.
No, not geography's not important, but like it's not about the steps you get there. It's just like theoretically.
Yeah.
Geography also is okay. Anyway, yeah.
There's gonna be geographers watching this video and be like, no, I'm not gonna watch this anymore. But anyways, yeah, it's real. For example, let's think of a different, not an actual butterfly effect, but something that's a butterfly effect which doesn't involve butterflies and hurricanes. What is a butterfly effect? Off the top of my head, okay.
I've got one.
Oh, go on.
Okay. Okay, yeah, I was watching this show, and there's this character who's like super powerful. He can go back and forwards in time, and he can see future events happening. He sees a car crash happening in the future, and so he goes to he goes to see what's happening, and then to stop that car crash actually happening, he removes a stone from the ground, right?
I get why it's something like this. Yeah. So there's a stone on the ground. Some guy kicks the stone goes and hits a cat, and the cat runs across the road, and the car has this swell.
Yeah, it's something along those lines.
Yeah.
So yeah, it's kind of the principle of the butterfly effect, but like the theory of it, obviously with the butterfly and the hurricane, it's a lot bigger. But the idea behind it is it's this sort of chaotic motion of the universe and unpredictability of the universe, and the idea that one tiny thing happening in one place could have sort of large knock-on effects. So I think it's an interesting idea, and I think the reason, like, if you go on IMDb now, you search butterfly effect, there's like so many movies and TV shows about it. And I think the reason for that, like the reason we're obsessed with this idea, is because it answers the question of whether like we can predict everything that's going to happen, and whether we can know for sure whether like if our actions or reasons or doubts about something can actually have impacts on the rest of the world. So I think for that reason, like it's not so much like a physics or a maths theory, but it's more of it's sort of an introspective idea of like, why do we want to know about this, and yeah. What do you think of it? I mean, okay, say where am I going with this?
Well, we always like, even with quantum mechanics and stuff in physics, something very chaotic, very fast, something that has like high amounts of entropy and stuff that we observe, they always end up creating something more stable. Actually, from GCSE, I've learned something. So this is sort of the idea of something chaotic causing order, right?
Mm-hmm.
Yeah. So I think it was something that the teacher said, eventually the universe will just have decayed just completely into just matter floating about doing nothing.
Yeah.
That's mad. But yeah, but imagine it went from something of such massive amounts of entropy right at the moment of the Big Bang, and then boom, death of the universe, or we'll call it the death. It's like everything's just floating about doing nothing.
Mm-hmm.
Which is mad.
Yeah. Actually, to do with chaos theory, which is kind of a part of the butterfly effect, but not really. But with chaos theory, it's a very simple, like, it's a very similar principle in that small changes to the initial conditions of a system can have massive repercussions. So if you look at a double pendulum system. So it's a pendulum, and then attached to that pendulum there's another pendulum, right? No, it's not two of them. It's one attached to the other.
Oh, okay. No, I get it. So as this one spins, it spins the other one.
Yeah, but like,
Okay.
did you know that if you let go of a double pendulum system, there is no way of predicting where it's going to go at all?
Damn.
You can try the maths. And I thought about this. I think Sachin told me first, like ages ago. And when you think about it, it's like, surely you can, right? Because like, you know the mass, you know its moments, you know its acceleration, and its like, sort of components of velocity and whatnot. Like, surely you could. But it's actually a chaotic system in that you don't know. There is no idea of knowing, especially in the long term, like over time. There is no way of knowing where it's going to go. And chaotic systems, like, you may think, oh, that's a very niche idea, but chaotic systems are actually just all around us. The air, fluids are chaotic, right? So you have chaotic flow and laminar flow. Laminar flow, say you have water, right? Laminar flow is like when you pour a glass of water from like a mug into a glass of water, like it's flowing and you can see it, right? It's moving like a line, right?
Mm-hmm.
I haven't lost you. Okay. Chaotic motion is the water when it's actually in the cup. If you look at the water in the cup, like it may appear that it's still, but it's actually moving in circles everywhere, right? It's the same thing with air. If you take a cross section of air and you like illuminate it with a laser, it's actually like the air is actually spinning around in different circles. These circles are called eddies. There's a whole different sort of field of maths with regards to the way that energy is transferred between eddies and stuff. But then if you look at the universe is a chaotic system. Like the universe, when you look at all these different shapes and of like galaxies and gas clouds and solar systems, it's all a chaotic system, right? So like chaos is like all around us, but like you said, like one of the great things about it is that chaos at such large scales can actually just create something very stable, which is something that laminar flow can't do. which I think is really cool.
You know what else is really cool?
What?
Car engines.
Okay, this is your line of thinking. I don't know where we're going with this, but
I don't know
wait.
either.
Actually, I have a really cool. You know, I was talking about the WHIM. Don't.
Yeah.
Have you seen a picture of it? Okay, obviously you haven't. You haven't heard of it. If you look at a if you look at a picture, search up WHIM, space, you'll find a picture. I'll put the pictures up on screen, but you'll find a picture of it, and then search up. Okay, you do that.
Yeah.
So you'll see sort of like an orange sort of like net, right?
Yeah, I do.
Which on its own is quite pretty.
It's actually really nice.
Yeah. But now search up map of neutrons in the brain.
Oh, I know. Yeah. Yeah. I see.
Neurons in the brain, not neutrons.
Not neutrons. Yeah. They're similar, aren't they? Yeah, it's the same network.
Yeah.
Actually, you know what's the thing? Mr. Smith said something in our biology lessons that's like observables. That sort of geometrical shape, almost hexagonal shape that I see with the WHIM. The WHIM. It's everywhere. It's literally like the favorite shape of nature. The hexagonal,
Is it?
like that sort of
On
polygonal
diamonds
shape.
in a hexagonal kind of shape as well, or graphite,
Diamonds.
carbon.
Yeah, so a lot of allotropes of carbon have that sort of
Yeah.
perfect sort of tetrahedral, or the nice geometrical structures, and you see that everywhere. It's like it's favored. It's favored by physics. So we're back. We had an interruption, but we are now past the interruption. Now the interruption doesn't exist anymore in our timeline. So let's continue.
Okay.
What the fuck did I just say? Anyways. So yeah, we're talking about shapes and the importance of certain shapes. And for your sake, I shall now draw a bending ring and show you how the 120-degree angle is created. So carbon, 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 hydrogen, and you have a fat ring. So, shit. That's my timetable. Hydrogen, carbon, carbon, carbon. 120-degree angle, because it's, that's an electron ring over there. So that's like a delocalized area of electrons, because benzene's a special kid. But this sort of like interact, that's one of the nice shapes. Another nice shape is if we observe the structure of diamonds. Put a carbon there, carbon there, carbon there, why not? There, there, and then this goes down there, there, there. Try my best to make it look neat. Man's not an artist.
I've seen diamond before. I know how it looks. Yeah. Okay.
Yeah, that was actually pretty nice. But that is the importance of shapes. It's an idea of, I guess it also adds to the teleological argument, and I guess that, because of how perfect these shapes are, how perfectly you observe the golden ratio and stuff.
You can argue that it's like the perfect shape, but in the grand scheme of things, like whilst we observe these shapes in certain places, could it not just be a coincidence, given the amount of shapes that there are in the world and in the universe, and the amount of structures there are, the amount of elements there are, the amount of like combinations of matter there is, could it not just be a coincidence that certain shapes just appear in different places, in the same way that it's a coincidence between the way that matter looks in the universe compared to the structure of neurons in the brain?
It can be, but it would be much cooler, much more sick if, for a specific reason, the efficiency of a certain lattice and a certain shape actually exists for some maybe surface area reason, a surface area to volume ratio or something. Or for example, like you see a catalyst in a catalytic converter, for example, of a car. You have the way that the platinum is sort of like placed is in a honeycomb lattice, and that lattice sort of maximize the surface area.
Mm.
Perhaps, yeah, each shape can have its own purpose, and via some sort of selection process, in a way that this the most efficient process is favored, just like natural selection. Is sort of picked in certain areas. That's more beautiful and something that I'd like to
Something you want to believe more.
Yeah, something I want to believe more than something just occurring due to chance, because chance is fucking boring.
Yeah, because again, though, with evolution is just a result of like random genetic mutations in DNA, or just hap chance of like an animal being in a specific place or being born at a specific time. So
the randomness, true.
But then again, it goes back to the idea of it's like in chaos theory, multiple chaotic systems balance out into something that's a lot more simple, right? In the same way, all this randomness creates a sense of like order in the universe. Like we look at evolution, it's like, yeah, you can see the logical sequence of how animals have developed, or in sort of the structure of benzene or carbon, you can see the reasons why it takes a hexagonal or tetrahedral shape or something. So all these sort of like chances and randomness, they can all come together and form something that's a lot more pretty or beautiful overall.
Yeah, there's a lot of images in medicine actually. They're just beautiful to look at because of the shapes and the different. Yeah, it's just
images of what?
The golden ratio. So, sort of, if you had immunofluorescence of certain certain stuff in the body. Recently, there was one. They were measuring hematopoietic cells that exist from the nose to like the neck, I think. And it was just really pretty. I don't know what it was. I couldn't read it at all. Like I was looking at it like cool colors. Whoa.
Yeah.
I felt like but I didn't actually understand it. But it just looked really nice.
Have you seen the Mandelbrot set?
I don't know what that is.
It's a set of complex numbers. I don't remember. There's a specific condition for it. But if you search up after this, and anyone who's listening can search up, if you search up the Mandelbrot set, like an explorer or something, and you can it's like the most amazing shape, and it's a fractal. You know what a fractal is?
No, I don't.
Oh, a fractal is it's a shape with a finite area but an infinite circumference. So it's sort of the area is sort of like a limit to infinity, but it has an infinite circumference in the sense that if you zoom in and in and in, it creates more shapes. Like you never finish. If today you take a triangle, you added 3 triangles to each side of the triangle. Outwards.
Sort
of. Inwards works too, but I think inwards you'd end up with an area of 0. But so outwards. And then to those outer triangles you add more triangles, and to each triangle you keep adding more triangles on each side.
Does it form a circle?
Kind of. It forms like a kind of snowflake pattern, and that has a finite area. But it has, if you try and measure it, you're just going to go on constant triangles, right? So then you'd end up with just an infinite circumference. And the 3D fractals are the most amazing thing. If you search up 3D fractal, it's I don't know what it is. It's just shapes and colors, but it just looks so cool.
We're gonna put it on the screen.
Put it on the screen. I'll put up a picture of the Mandelbrot set and 3D fractals. But I think they're the coolest part of math. They're so sick, and you get fractals naturally occurring in science. The formula that you use.
I'm looking at one right now. It looks like a neuron.
Yeah, but it's a fractal. It's a never-ending shape. And some fractals never repeat. I don't know, but I think the Mandelbrot set doesn't repeat. But I have to... it repeats on the x-axis, on the real axis, but I don't think it repeats on the imaginary axis. But anyway. And you find fractals in nature, right? So the Mandelbrot set, it's a set of complex numbers. You can derive the Mandelbrot set from a formula that can predict the growth of a population over time, right?
the Mandelbrot set, I'm looking at it right now.
It's like a heart
It
shape.
looks like... That's mad. It looks like a snowflake almost.
Yeah. And it's like I'll maybe we'll go into it later at some point, but it's like it's the coolest shit, and yeah, it's so sick.
But yeah, maybe there's the intelligent designer that's designing these very, very nice shapes to look at, and that leads us on to next week, where we're going to talk about God, theology, different, and we're going to have guests on and everything. So until then, in a bit, like, comment, subscribe, and all of that. So bye.
Okay, bye.